Hi everyone, we are in the midst of our section on derivatives. Last week we covered derivatives at specific points, and today we're going to introduce the notion of derivative functions. As we've seen in earlier presentations, the rate of change, or if you prefer the derivative, of a function f of x at coordinate point a f of a is obtained from using either this first limit definition, which takes into account the change in height, f of b minus f of a, over the change in x, b minus a, as we let b head towards a. Or the alternative limit definition of the derivative, where h, which represents the separation between 2 points, is becoming closer and closer to 0. The numerator, f of a plus h minus f of a, still represents the change in y over h, which is still the change in x. The problem with these two formulas is that if we decide to change the location of the point on the curve, these limits have to be recalculated over and over again, unless we can find a way to avoid these recalculations and still find the tangent line slope at different points. That's actually what the role of the derivative function is. So its name already kind of gives you a hint as to the fact we are not going to get a specific number, but rather a function, a recipe, with which we will evaluate the derivative. The derivative function is defined as f prime of x. So this time, rather than specifying the point, which we denoted by a earlier, we will leave that point as an unknown. It's still going to be considered as a fixed point, whereas b will be the point moving towards it. Alternatively, we can find f prime of x using the second limit definition, where rather than having f of a plus h minus f of a, we're going to use f of x plus h minus f of x as the change in y. Graphically, the only difference between the derivative function and derivatives at a point that we did in preceding videos is that x, the point that we are attracting our attention to, is not specified, but we still treat it as being a fixed point. b, f of b, is the point that we will move closer to x, f of x, through the limit process. The alternative definition simply uses a second point, x plus h, that is, h units to the right or to the left, depending on the sign of h, from the fixed point x, f of x. So essentially this is the exact same process we've been doing, except for the fact that the fixed point, a f of a, is replaced by an arbitrary point, x f of x. For example, let's find the derivative function for f of x equals x squared. I'm going to be using the first limit definition in order to find this derivative function. So f prime at x is the limit as b heads towards x of the difference between f of b and f of x, so the change in y, over b minus x, the change in x. Applying the rules that apply for f of x and f of b, we have b squared as the value of f at b, and we have x squared as the value of f of x. So b squared minus x squared over b minus x as b moves towards x. This is obviously a 0 over 0 form, which we can solve through factoring and cancelling. So at the numerator, a difference of squares appears that leads to common b minus x's, which can be eliminated, and the resulting expression b plus x has a limit value that will head towards 2x when b is replaced by x through direct substitution. Here's what we're getting. We're getting a specific rule, a derivative function, that will give us the slope of function f at a point that we'll eventually specify. So f prime of x is equal to 2x. We're going to see later how we can apply this rule. For those who are curious about the second limit definition, it should obviously give the same answer. We're calculating the same thing. So here is the second limit definition. X plus h is the location of the function where we are evaluating x squared. So rather than having x, x plus h plays the role of the argument and is therefore squared. F of x is x squared itself. And we're going to have to evaluate this difference in height at the numerator over the difference in x, which is h at the bottom. We don't have much choice here but to do some expanding. So we're going to FOIL the squared term x plus h. Recognize that x squares are added and subtracted and eliminate them. And although this is also a 0 over 0 form, the h at the numerator can be factored and eventually cancelled off. So all that remains is an expression 2x plus h, and as h heads towards 0, 2x will be the outcome. This is the exact same result that we had using the other limit definition. Okay, so just to summarize what we're actually doing here, we have found a function which gives us the derivative of f at any arbitrary point. So for instance, if you wish to calculate the slope of function f at minus 2, you would replace x by minus 2 in the derivative function you've just obtained and get minus 4. So here's your graph of x squared. The function's value at minus 2 is 4, so that's the y-coordinate. Remember that the derivative doesn't give you the y-coordinate, it only gives you the slope. And according to the work we've just done, the slope, f prime, at minus 2 should be minus 4, which seems to agree with our picture. Here's what's convenient about having a derivative function. If I decide to recalculate f prime at 1, I will replace x by 1 in the derivative function and realize that the slope of f at 1 is equal to 2. Here's the same quadratic expression. When x is 1, y is 1, that's the y-coordinate, and the slope of the line tangent to the curve at this point would be 2. Same thing, if we replaced x by 0, we'd notice that the function's slope is 0. Okay, so obviously the parabola for an x value of 0 is equal to 0, and here is its tangent line with a slope of 0. So we're talking about a horizontal tangent line here. Okay, applying the same definition to a different function. For instance, here the derivative of the function root of x. Now remember, a root function has a domain that consists of x's that are greater or equal to 0. So we wouldn't think of doing the derivative either at 0 or left of it, because we would be at the extremity or outside of the domain. Okay, so according to the first limit law, or the first limit definition of the derivative, we would have to calculate the root of b minus the root of x, which are the values of f of b and f of x, respectively, over b minus x. And the limit process will turn this average rate of change into the instantaneous rate of change. The 0 over 0 form that we had in the previous step can be cancelled off or solved by using rationalization. So I'm multiplying above and below by the conjugate of root of b minus root of x. By expanding, a common factor b minus x is obtained and can then be eliminated. As b heads towards x, the quotient 1 over root b plus root x will turn into 1 over 2 root of x. And here is our rule for any derivative of this function calculated at an arbitrary point x. Let's check if this seems to make sense. So I've graphed the function y equals root of x. At the top of our slide, we see our recipe or our formula to find the derivative at any given point. If we calculate f prime at 1, we'll notice a half should be the slope of the tangent line. When x is 1, the function's value, root of 1, is equal to 1, and here is its slope, which definitely fits with the numerical value 1/2 that we found. Moving to a different point on the curve, let's say 4, the root of 4 is equal to 2, so that's where we're looking on the curve. The formula, or the derivative function, tells us we have to expect a slope of 1/4, which again seems to fit with what we're getting graphically from the tangent line slope. One last example. Here's a rational function, f of x equals 1 over x squared, always using the same definition, which happens to be more convenient for the most part when it comes to polynomials, rationals, and radicals. So f of b minus f of x will convert into 1 over b squared minus 1 over x squared. Over the change in x is b minus x. Before trying to eliminate the 0 over 0 form, we're probably better off simplifying the fractions, which I've chosen to do by multiplying by b squared x squared, both top and bottom. Expand b squared times x squared to the numerator's expression, and leave b squared x squared as a factor of the denominator. At the numerator, we see a difference of squares, x minus bx plus b. And at the bottom, just for convenience, I factored out the sign from b minus x to make the x minus b's more obviously simplifiable. So here we go, we've simplified the x minus b's. And now, for every b that becomes x through the limit process, we will get 2x at the top and minus x to the power 4 at the bottom. We can then reduce the common x's to get our recipe, the derivative function for f of x equals 1 over x squared. Graphically once more, the graph that appears in front of you is the graph of y equals 1 over x squared. According to our rule, the slope at any point on this curve should be given through the derivative function minus 2 over x cubed. So let's check. According to this formula, the slope of the function at 1 should be minus 2. Now remember, when x is 1, the function's value is 1 over 1 squared. So the position on the graph is at position 1, 1. Its slope is what the derivative is measuring. And it certainly looks like minus 2 is an appropriate number to represent that rate of variation. Calculating at minus 2 brings us into the second quadrant. So here is the function's value at minus 2. That would be 1 over minus 2 squared, so 1/4. And according to the derivative function, the slope of the tangent line should be 1/4. Again, matches the graph. The graph is increasing when it crosses the point that is highlighted at minus 2, and therefore the formula seems to work out very nicely. So we could essentially change the value of x to fit the position where we wish to evaluate the slope without having to recalculate limits for every one of those points. Now, if you've been paying close attention, you may have observed a certain pattern developing. Here are the 3 derivatives that we have done in this particular video. And expressed as powers, you may have noticed that x squared, once differentiated, became 2x to the 1. X to the half became half x to the minus half. The derivative of x to the minus 2 became minus 2x to the minus 3. In all of these cases, the same pattern has been repeated. The exponent has become the coefficient in the derivative, and the derivative's exponent is 1 less than it was before. This is what we call the power rule. X to the n is differentiated to give n x to the n minus 1.